If someone asked you right now how fast you are moving, the answer would seem obvious. You look around, notice that everything is still, and conclude that you're not moving at all. The chair beneath you isn't sliding across the floor. The walls aren't rushing past your eyes. The floor remains as solid and still as it has always seemed. This moment smells of complete stillness. This feeling is an illusion. At this very second, as this sentence finishes being spoken, you are taking part in one of the most boundless journeys there is. You are traveling through space at such high speeds that the human mind stumbles when trying to grasp them. In the time it took for this sentence to be spoken, you have already traveled thousands of kilometers through the universe without going anywhere. And the strangest thing is that you don't feel any of it. Nothing. No sensation at all. No vibration, no wind on your face, no sign that the ground beneath your feet is actually a vehicle speeding along. The story of how you really move through the cosmos begins with one of the greatest misconceptions in human history. The belief that the Earth stands still at the center of everything. For thousands of years, this assumption seemed too obvious to be questioned. Every day the sun would rise. Every day it would set. The stars seemed to revolve around whoever looked up. The moon crossed the sky overhead. Everything seemed to move, while the Earth remained still. It was a conclusion that made perfect sense from the perspective of everyday life. After all, on a calm beach, looking at the horizon, the ground beneath your feet feels solid, and nothing suggests that it's the surface of a giant sphere speeding through space. Reality, however, was stranger than anyone imagined. The first crack appeared when astronomers began to observe the movement of the planets with more precision. Some celestial bodies refused to behave as they should if the Earth really occupied the center of the cosmos. The movements became tangled, confusing. Some planets even seemed to reverse direction in the sky, moving backward for a while before resuming their course. The universe seemed too complicated, almost artificial. That's when a revolutionary idea emerged. What if Earth wasn't the center of anything? What if the Earth itself was in motion? Nicolaus Copernicus, in the treatise on the revolutions of the celestial spheres, published in 1543, was the one who organized this idea into a coherent mathematical system, placing the sun, not the Earth, at the center. Decades later, Johannes Kepler refined the calculations and described the orbits not as perfect circles, but as ellipses,
solving much of the confusion that troubled ancient astronomers.
Today, that idea seems obvious. You learn that in school. You see animations of planets orbiting around the sun. You grow up accepting that as a basic fact of science. But there's something unsettling about trying to hear that news for the first time without the comfort of familiarity. To discover that the whole world beneath your feet spins like a giant wheel, that this same world moves around the sun at the same time, that the sun itself moves through the galaxy, and that the galaxy also moves. Suddenly, the comfortable image of a quiet and stable Earth disappears. In its place, a universe emerges where everything moves, everything orbits, everything travels. So the inevitable question is, at what speed are you really going? The answer starts with the Earth itself. The planet completes a full rotation on its own axis about every 24 hours. Since the Earth is a sphere, the speed of this rotation changes depending on the point on the globe. Near the poles, this speed is low. Near the equator, things get astonishing. At the equator, a person is moving at about 1,670 kilometers per hour simply because the planet is spinning. This means that someone standing near the equator is traveling faster than many commercial airplanes without doing absolutely anything. A commercial airliner accelerates down the runway until it reaches cruising speed, which is around 900 kilometers per hour. The Earth spins. It spins. The Earth's rotation at the equator surpasses that and keeps up this pace continuously, day and night, every second of an entire lifetime. No one notices. There is no sensation of rushing through space. No strong wind generated by this movement. No sensation of movement. The explanation lies in a principle that shapes almost everything you experience. Movement by itself is usually invisible. What you actually feel is the change in speed, not the speed itself. When the plane accelerates during takeoff, your body is pushed against the back of the seat. When a car brakes suddenly, your body is thrown forward. When the elevator starts to go up, there is a brief sensation of force. But as soon as the movement becomes steady and smooth, these sensations disappear. I spent years thinking this detail was strange. A passenger inside a stable airplane, flying at hundreds of kilometers per hour at cruising altitude, completely forgets that they're moving. The movement becomes invisible because everything around shares the same speed. The Earth works exactly like that. The atmosphere rotates along with the planet. The oceans rotate along with it. Every building, mountain, tree, animal, and human being rotates along with it. Since everything moves together, this tremendous speed becomes impossible to detect in everyday experience. This same idea is that no experiment conducted within a reference frame that moves smoothly and constantly can reveal this motion by itself. It had already appeared in a thought experiment described by Galileo Galilei in the Dialogue Concerning the Two Chief World Systems, published in 1632. He imagined an observer locked inside the hold of a ship, sailing on a calm sea, butterflies flying, fish swimming in an aquarium, drops of water falling. Nothing inside that closed hold would reveal whether the ship was standing still in the harbor or gliding smoothly across the sea. Richard C. Feynman revisited this same idea in the Feynman Lectures on Physics when explaining why no local experiment performed inside a system in uniform motion is able to reveal that motion. It's not just a figure of speech, it's a physical principle, tested and confirmed for 400 years. And you're living inside it right now without even noticing. But the Earth's rotation is just the first layer of this journey. The next one is much more dramatic. While the Earth spins on its own axis, it also orbits the Sun, tracing a gigantic path around the star every year. To complete this journey, the Earth needs to move at an extraordinary speed. The number almost sounds implausible. The Earth moves around the Sun at approximately 107,000 kilometers per hour. That's equivalent to almost 30 kilometers per second. In the time it took to say that sentence, the Earth has already traveled dozens of kilometers through space, orbiting a star that's about 150 million kilometers away. No vibration, no turbulence, no sign that the whole world is engaged in a never-ending race around a distant nuclear furnace. For much of human history, that would have sounded far too implausible. A planet that spins and also races around a star at more than 100,000 kilometers per hour already sounds like fiction. But the deeper scientists looked into the universe, the more puzzling the picture became, because the Sun itself refuses to stay still. The star is not sitting still in the sky, in a calm cosmos. It is engaged in its own monumental journey around the Milky Way. And as soon as this layer of movement comes into play, the speeds become almost impossible to imagine. To understand what's next, you first need to zoom out from the solar system and see where the Sun really resides within the vast structure of the galaxy. The moment the scale of the solar system is left behind, something curious happens. The speeds that once seemed implausible start to seem small. A few thousand kilometers per hour were impressive when it came to the Earth's rotation. 107,000 kilometers per hour sounded enormous when it came to orbiting around the Sun. Even so, these numbers belong to a much larger system, which in turn moves through space at an even more astonishing pace. If the entire solar system were reduced so that Neptune's orbit fit inside a small coin, the planets, the moons, the asteroids, the comets, even the icy bodies at the distant edge of the solar system would occupy a tiny region compared to the immense structure around them. This structure is the Milky Way, the cosmic home, a vast collection of stars, gas, dust, dark matter, and countless planetary systems stretching for about 100,000 light-years. Within this colossal galactic city, the Sun is not at the center. In fact, it occupies a relatively ordinary position halfway between the galactic core and the outer edge. If the Milky Way were a gigantic spinning wheel, the Sun would be one among billions of stars carried by this rotation, orbiting the center just as the Earth orbits the Sun. This is where the numbers start to leave common intuition behind. The Sun travels around the center of the Milky Way at approximately 828,000 kilometers per hour. The Earth's orbit around the Sun, which already seemed dizzying, is just a small component within this much greater journey. The entire solar system, every planet, moon, asteroid, comet, the Sun, space probe, and every human being is racing around the galaxy at a speed approaching 1 million kilometers per hour. If it were possible to observe the Milky Way from far away, the movement would look breathtaking. Vast spiral arms would sweep through space smoothly, while hundreds of billions of stars would follow their own paths around the galactic center. Among them would be the Sun, carrying the Earth on a journey so immense that a single complete orbit takes approximately 225 million years. This means that the last time the Earth occupied this same position within the galaxy, dinosaurs still ruled the planet. The Himalayas had not yet fully formed. The Atlantic Ocean was younger than it is today. Human beings did not exist. The human species, in fact, has never completed a full orbit around the Milky Way. Our species emerged just a tiny fraction of a galactic year ago. Every civilization, every kingdom, every language, every scientific discovery, every war, every religion, and every technological achievement, all of it unfolded within a very small slice of our first trip around the galaxy. Seen from this perspective, the entire history of humanity starts to seem too short to be taken as seriously as it usually is. Even so, the Milky Way also refuses to stand still. For a long time, galaxies were imagined as isolated islands, quietly floating in the darkness. The reality turned out to be much more dynamic. Galaxies interact, influence each other through gravity, form clusters, merge, collide, and wander through cosmic structures so vast that they almost defy any attempt at visualization. As astronomical instruments became more powerful, scientists discovered that the Milky Way itself moves through space at an extraordinary speed. Part of this movement comes from its relationship with neighboring galaxies. The most famous example is Andromeda, the largest galaxy near ours. Located about 2.5 million light-years away, Andromeda has been slowly approaching the Milky Way. Billions of years from now, the two galaxies will merge, creating an entirely new galactic structure. But Andromeda is just one piece in a much bigger picture. The Milky Way belongs to a collection of galaxies known as the Local Group, dozens of galaxies bound together by gravity, taking part in a slow cosmic dance that has lasted for billions of years. And even the Local Group isn't standing still. It's moving through space as part of an even larger structure called the Virgo supercluster. And again, the numbers become breathtaking. The galaxy is moving through the universe at hundreds of kilometers per second, not per hour, per second. At this point, the very concept of standing still starts to lose any meaning. Everything you associate with stability ends up being part of an endless chain of movement. The Earth revolves around the Sun. The Sun revolves around the galaxy. The galaxy moves through intergalactic space. Even larger structures move relative to each other on such vast scales that even light takes millions of years to cross them. What makes this realization particularly strange is how completely invisible it remains. Looking around the room where you are right now, nothing seems out of the ordinary. Nothing seems to be hurtling through space. The coffee cup is still. The walls are still. The floor beneath you is still. Every sensory experience suggests absolute stillness. Even so, if someone could draw your actual path through the universe, the result would look nothing like the simple circular orbit shown in textbooks. Many illustrations show the Earth orbiting the Sun as if the Sun itself remained fixed in place. In reality, the Sun is continuously moving through the galaxy while the Earth revolves around it. The result looks like a complex spiral twisting through space. When you add the movement of the galaxy, this trajectory becomes even more complicated. You are not standing still. You follow an intricate path through a moving universe. A path that began long before you were born and will continue long after you are gone. The deeper scientists investigated these movements, however, the more intriguing the universe became. Because eventually, astronomers realized that even after adding up the movement of the Earth, the Sun, the Milky Way, and the neighboring galaxies, there was still something missing in the equation. It was as if an invisible force was pulling entire regions of the universe toward a destination that no one could fully explain. And this discovery would lead researchers to one of the strangest mysteries in modern astronomy. For much of the history of science, the question of motion seemed relatively simple. Objects moved because something pushed them. Planets moved because they orbited stars. Stars moved because they orbited galaxies. Galaxies moved because gravity influenced their trajectories. The details could be complicated, but the overall picture seemed understandable. Then, astronomers began to observe the universe on the largest scales ever studied. And suddenly, something strange appeared. When scientists measure movement in everyday life, they always compare one object to another. A car moves in relation to a road. An airplane moves in relation to the ground. A planet moves in relation to its star. Movement, by nature, is usually relative. And what if you wanted to measure movement in relation to the universe itself? At first glance, that sounds impossible. After all, what would serve as a universal point of reference? The universe doesn't have an obvious center. There isn't a giant cosmic landmark sitting in the middle of everything. Nature, however, has offered something surprisingly close to that. To understand, we need to go back almost 14 billion years in time, to a time before stars, before galaxies, before planets, before anything remotely like the universe we know today. The primordial universe was hot in a way that's almost impossible to describe. The temperatures were so extreme that matter, as we know it, simply couldn't exist. Atoms couldn't form. Light itself had trouble traveling freely because particles were constantly colliding with each other inside a dense cosmic fog. The universe wasn't dark, but it wasn't transparent either. Light existed everywhere, but it was trapped. Then, about 380,000 years after the Big Bang, something remarkable happened. The universe expanded and cooled enough for atoms to form. Suddenly, light was able to travel freely. The cosmic fog cleared, and a vast sea of radiation began a journey that continues to this day. That ancient light still fills the entire universe. It comes from every direction, surrounds every galaxy, and passes through every region of space. And although it has cooled drastically over billions of years, astronomers can still detect it. Today, this echo is called the cosmic background radiation. Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs, accidentally discovered this radiation in 1965 while trying to eliminate persistent noise in a radio antenna. They published the discovery in 2 short pages in the Astrophysical Journal, not knowing at first that they had just detected the oldest light ever recorded by science. Imagine a huge cathedral, long after the choir has finished singing. The voices are gone, but a faint echo still lingers, resonating throughout the entire structure. The cosmic background radiation is something similar, an ancient echo from the young universe, still present almost 14 billion years later. And since this radiation fills space in all directions, it gives astronomers something extremely valuable, a frame of reference against which motion can be measured. When scientists studied this ancient light, they expected it to look almost identical in all directions. For the most part, it is, but not perfectly. One side of the sky appeared slightly warmer. The opposite side appeared slightly colder. The difference was tiny, but unmistakable. The explanation turned out to be simple and unsettling at the same time. The Milky Way was moving. More precisely, the galaxy, the solar system, the planet, and every human being on it were traveling through the universe in relation to this ancient radiation. Once the measurements were completed, the astronomers discovered something remarkable. The solar system moves in relation to the cosmic background radiation at approximately 2,100,000 kilometers per hour. Not because the Earth rotates, not because the Earth orbits the Sun, not because the Sun orbits the Milky Way, but because the entire galactic neighborhood is moving through the universe itself. I confess that this part makes me feel unsure every time I try to explain it properly. I can repeat the number, 2,100,000 kilometers per hour. But truly understanding what that number means is a completely different story. Human intuition was never built to process speeds measured in millions of kilometers per hour. Maybe a different perspective will help. If you froze time and observed Earth from far away, from deep space, you would see the planet spinning on its own axis while orbiting the Sun. You would see the Sun orbiting the center of the Milky Way. You would see the Milky Way moving in relation to the neighboring galaxies. And you would see all this combined movement carrying everything through the universe at a speed greater than 2 million kilometers per hour. Even this picture is still incomplete because astronomers eventually discovered that this movement seemed to be pointing towards something. Something monumental, distant, something that would beat the most intriguing names in modern astronomy. The Great Attractor. When scientists mapped the movement of galaxies across vast regions of space, they noticed a pattern. Large groups of galaxies seemed to be drifting toward a particular area of the sky. It was as if a colossal gravitational influence was pulling entire galactic structures in the same general direction. The more observations accumulated, the harder it became to ignore the pattern. Something massive seemed to be waiting there, with enough gravity to affect the movement of countless galaxies spread across hundreds of millions of light years. Naturally, the astronomers wanted to see this thing directly. There was just one problem. They couldn't. The region was behind the dense plain of the Milky Way, a strip of the sky packed with stars, gas, and dust, which obscured much of what was behind it. For years, the object responsible for this colossal gravitational pull remained hidden from direct observation. That was exactly the situation faced by the astronomers. How can you notice that the leaves of an entire forest are being blown toward a specific point while a mountain prevents you from seeing what's there? Something must have been happening, something causing that movement, but the source remained hidden. Sandra Faber, Alan Dressler, David Bernstein, Roger Davies, Donald Lyndon Bell, Roberto Terlevich, and Gary Wagner. A group of 7 astronomers, who became informally known as the Seven Samurai, identified this flow of galaxies in 1986. By analyzing the distances of more than 400 elliptical galaxies and comparing them with the redshift of each one, the result pointed to a huge concentration of mass located at an estimated distance between 150 and 250 million light-years, pulling the local group and a large part of the Virgo supercluster in the same direction. Only in the following decades, with X-ray observations capable of penetrating galactic dust, were astronomers able to identify the Norma cluster as the most likely core of this mass concentration. Even though the Great Attractor, as we now know, is not a single object, but rather part of an even larger structure called the Laniakea supercluster. What at first seemed like a single destination slowly turned into something much more complicated. And maybe that's exactly the pattern of the universe. Every time it seems like the final answer has been found, that answer expands into a bigger question. The Earth was not the center of the solar system. The solar system was not the center of the galaxy. The Milky Way was not the center of the universe. The Great Attractor was not the final destination. The deeper you look, the larger the structures become. The farther you travel, the more horizons appear. And nowhere is this more evident than when examining the colossal architecture of the cosmos. A network of galaxies and superclusters so vast that even the Milky Way starts to seem surprisingly small. One of the difficulties in trying to understand the universe is that the human mind constantly tries to shrink everything down to a manageable size. Comparisons, patterns, familiar reference points, because the alternative is almost too overwhelming. Whenever astronomers announce the discovery of a massive galaxy cluster or a gigantic cosmic structure stretching across hundreds of millions of light years, most people hear the numbers, recognize that they're big, and file them away mentally. In the same category, vague astronomical distance, just too huge to really think about. The problem is that the universe doesn't scale in a way that human intuition can comfortably keep up with. The difference between a city and a country is already significant. The difference between a country and a continent is huge. The difference between a continent and an entire planet is hard to fully appreciate. Even so, these differences become almost insignificant compared to the leaps in scale that happen throughout the cosmos. When the conversation was about Earth's orbit around the Sun, the numbers revolved around millions of kilometers. When we move on to the nearest stars, these distances already jump to trillions of kilometers. Then comes the Milky Way, where distances start being measured in thousands of light years. Next come the galaxies, separated by millions of light years. Then, the galaxy clusters, spanning tens of millions of light years. Then, the superclusters, stretching for hundreds of millions of light years. At each new level, the scale increases so much that the previous level starts to seem small. As astronomers mapped increasingly larger portions of the observable universe, they began to notice that galaxies were not randomly distributed throughout space. On the contrary, they seemed to organize themselves into immense structures, resembling a kind of cosmic architecture. Clusters of galaxies connected to other clusters through gigantic filaments of matter. These filaments stretched across such vast distances that light itself would take hundreds of millions of years to cross them from end to end. Between these structures, there were enormous voids, regions where comparatively few galaxies could be found. If it were possible to zoom out far enough to see the largest structures currently observable, the universe would begin to resemble a vast, three-dimensional web, suspended across distances almost impossible to visualize. This arrangement became known as the cosmic web. Every galaxy ever photographed, every star that has ever shone in the night sky, every planet that might harbor life, every black hole, nebula, and stellar nursery exists somewhere on this cosmic web. The Milky Way itself is just a tiny component within a filament that in turn is a small part of a much larger structure. The more scientists investigated these patterns, the more puzzling the picture became. Entire superclusters containing tens of thousands of galaxies appeared connected across vast distances. Massive concentrations of matter exerted gravitational influence over regions so large that ordinary human experience offers no meaningful comparison. It was as if the universe had built a structure on such an immense scale that entire galaxies became equivalent to small cities scattered across an entire continent. Even these colossal structures may not necessarily be the largest things in existence. One of the fascinating aspects of modern astronomy is that it continually forces scientists to question where the real limits lie. Every time researchers believe they have identified the largest structure in the universe, better observations often reveal something even larger just beyond it. New surveys discover additional galaxies. Larger maps reveal patterns that were previously hidden. More powerful instruments extend the observable horizon even deeper into the darkness. The James Webb Space Telescope contributes to this process in its own way. Although it was not specifically designed to map gigantic cosmic structures, its ability to detect extremely distant galaxies provides valuable information about how these structures have evolved throughout cosmic history. By observing galaxies whose light began its journey billions of years ago, astronomers gain a window into what the universe was like in earlier stages of its development. In many ways, this telescope functions like a historian, examining ancient civilizations. Most historians can't travel to the past and observe events directly. Instead, they reconstruct history from evidence that has survived. Fragments of buildings, ancient documents, inscriptions, artifacts, and ruins allow us to piece together stories that unfolded a long time ago. Astronomers operate in a similar way. The galaxies observed by James Webb are not simply distant objects. They are historical records. In May 2024, Brent Robertson and the JADE survey team announced the discovery of a galaxy existing just 300 million years after the Big Bang, an almost primordial moment in cosmic terms. Listed in the team's catalog under a technical acronym, it would later be remembered as the most distant galaxy ever confirmed up to that point. What surprised the researchers was not just the distance, it was the size and brightness of the galaxy. More than 1,600 light-years in diameter, producing light mainly from young stars and not from a supermassive black hole devouring matter around it. Such a large and luminous structure was not expected so early in the history of the universe. Existing models of galaxy formation had to adjust to accommodate this discovery. For many years, scientists expected the first galaxies to be relatively simple, small, and disorganized. Instead, the James Webb has revealed galaxies that are surprisingly bright, surprisingly mature, and in some cases, surprisingly massive for their age. These discoveries have sparked intense debate because they suggest that certain aspects of cosmic evolution may have happened at a faster pace than previously believed. It's important to understand that discoveries like this don't mean that scientists were completely wrong before. Reality is usually more subtle than that. Scientific models aren't sacred texts, they're tools. Their purpose is to describe reality as accurately as possible, using the evidence available at the time. When new observations arise, the models evolve. Sometimes the adjustments are small, sometimes they are significant. Either way, the process brings understanding closer and closer to reality. And reality keeps surprising us. In fact, one of the most striking lessons of modern astronomy is that the universe usually seems more inventive than the theories anticipate. Structures appear where they weren't expected. Patterns emerge where randomness was supposed to exist. New observations reveal details that no one predicted with complete accuracy. This constant process of discovery creates a strange feeling when contemplating the place we occupy within the cosmos. On one hand, humanity has achieved something monumental. A species that evolved on a small rocky planet now has instruments capable of studying galaxies whose light began traveling toward us billions of years before Earth even existed. We have already measured the movement of stars, mapped the structure of our own galaxy, detected planets orbiting distant suns, and begun to reconstruct the history of the observable universe. On the other hand, each major discovery seems to reveal how much still remains unknown. The farther we look, the bigger the universe gets. The more we learn, the more questions arise. The horizon never stops receding. And perhaps nowhere else does this feeling become stronger than when asking a deceptively simple question. If everything is moving, if galaxies are moving, if clusters are moving, if superclusters are moving, if the entire observable universe is evolving, what exactly does motion mean on the largest possible scales? Going back to the question that started this journey, how fast are you really traveling through the universe? The answer ends up being much more complicated than just a simple collection of huge numbers. Each layer revealed a greater speed than the previous one, but each new layer also brought a deeper realization. Movement within the universe isn't organized into separate categories. It's not as if one journey ends so that another can begin. Instead, each movement happens simultaneously, nested within the next, like an endless series of circles expanding until they disappear on scales beyond common understanding. This becomes especially fascinating when we look at what astronomers have discovered about the universe itself throughout the 20th century. For thousands of years, the cosmos was imagined as something permanent and unchanging, a vast stage upon which stars, planets, and galaxies moved. Even after the discovery that the Earth orbited the Sun, and that the sun orbited the galaxy, many people still imagine space itself as something fundamentally static. The objects within it moved, certainly, but the universe as a whole remained fixed. Then, observations began to reveal a completely different reality. As telescopes improved over time, and astronomers began to measure increasingly distant galaxies, a remarkable pattern emerged. The galaxies seemed to be moving away from each other. And the farther away a galaxy was, the faster it seemed to be moving away. Edwin Hubble published this relationship in 1929 by comparing the distance of galaxies with the rate at which their light shifted toward red, which later became known as Hubble's law. At first, this is hard to understand because intuition naturally imagines galaxies traveling through empty space, like ships crossing the ocean. The truth, however, is stranger than that. What scientists gradually realized was that the distances between galaxies were increasing because space itself was expanding. The fabric of the universe was stretching, carrying immense structures farther and farther apart over time. One way to gauge how unusual this idea really is: countless dots drawn on the surface of a balloon move away from each other as the balloon is filled with air. Not because the dots are crawling along the surface, but because the very surface that connects them is expanding. The universe is not literally a balloon, but the analogy helps illustrate a profound idea. Galaxies are often separated not just by moving through space, but by the expansion of space itself. The more astronomers studied this phenomenon, the more astonishing it became. For a long time, many researchers assumed that gravity would gradually slow down this expansion. That expectation seemed reasonable because gravity pulls matter together. So, if the universe started expanding after the Big Bang then, the combined gravitational influence of countless galaxies should, over time, act as a brake, gradually slowing down the rate of expansion over billions of years. Instead, the opposite seems to be happening. Careful observations have revealed that the expansion of the universe is accelerating. The distances between immense cosmic structures are increasing faster and faster, as if some mysterious influence is pushing the universe outward on the largest scales. Adam Rees, Saul Perlmutter, and Brian Schmidt independently led the two research groups that reached this conclusion in 1998 by observing distant supernova explosions. This discovery earned the three of them the Nobel Prize in Physics in 2011. This discovery is among the most surprising scientific findings of modern times, because it introduced a phenomenon that no one fully understands to this day. This unknown influence was named dark energy. Even so, giving something a name is not the same as understanding it. The label only acknowledges that there is an ongoing process whose true nature remains one of the greatest mysteries in all of science. I'm not going to pretend that I completely understand this. No one understands, not really. Not even the physicists who spent their entire careers studying the subject. There is a way of thinking about it that at least makes the strangeness interesting instead of paralyzing. What makes this phenomenon particularly fascinating is that dark energy seems to dominate the future of the cosmos on a large scale. The stars, the planets, the galaxies, the black holes, and everything else we can directly observe represent only part of the story. The universe contains forces and components that remain largely invisible to us. And even so, these hidden elements may end up determining the fate of everything we know. At this point, the original question about your speed begins to turn into something even deeper. At the beginning of this journey, The attempt was to find out how fast the Earth moves, how fast the solar system moves, how fast the Milky Way moves. Now, the realization is that the universe itself is constantly evolving. You are not just a passenger on a planet orbiting a star. You inhabit a cosmos whose structure changes over periods of time that are almost incomprehensible. The very stage itself moves beneath the actor's feet. And perhaps it is exactly here that the true strangeness of this story reveals itself. Most people go through their whole lives with the feeling that they are standing still. The ground beneath their feet seems stable. The horizon seems fixed. The sky above seems calm and familiar. Hidden beneath this everyday experience, however, lies a reality of almost incomprehensible dynamism. At this very moment, the Earth is spinning. The Earth is orbiting the Sun. The Sun is orbiting the Milky Way. The Milky Way is moving through a vast network of galaxies. The local group is drifting through even larger cosmic structures. The observable universe continues to expand. Each of these processes happens simultaneously, and each of them contributes to this boundless journey we call existence. The most remarkable thing is not just that these movements exist, it's that a species evolved on a small rocky world somehow managed to discover them. Human beings emerged with no knowledge of galaxies, black holes, dark matter, or cosmic expansion. Our ancestors looked at the night sky and saw points of light. They had no way of knowing that those lights were suns. They had no way of knowing that those suns belonged to a galaxy. They had no way of knowing that this galaxy was just one among billions. And they certainly had no way of knowing that everything around them was moving through a universe whose scale is beyond ordinary imagination. Still, step by step, generation after generation, humanity kept asking questions. People built observatories. They developed mathematics. They invented telescopes. They launched space probes. They created instruments capable of studying light that began its journey billions of years before Earth existed. And through these efforts, they discovered one of the most extraordinary truths ever revealed. The universe is not a quiet place. It is not a static place. It is not a setting where objects simply remain still against an eternal background. It is instead a vast and evolving system, filled with movement on every conceivable scale. From the rotation of planets, to the drift of galaxies, to the expansion of space itself, every second of your day, without the slightest sense of movement, you are part of this system. You are being carried by processes that began long before human civilization existed and will continue long after it disappears. I've started to look at the night sky differently since I understood this whole chain of movement. I no longer see a dark ceiling dotted with still lights. I see layers of speed nested within each other. The Earth spinning, the sun racing through the galaxy drifting through an ocean of other galaxies, and space itself stretching beneath all of this. There's still a part of this that leaves me uncertain. I can never actually feel this movement myself, even though I know the numbers. The mind accepts it, but the body remains convinced that it's standing still. Maybe that's the most honest part of the whole story, to understand something precisely and still not be able to fully feel it. Perhaps the most disarming realization of all is that, despite all this accumulated knowledge, humanity might still be just at the beginning of this story. Future generations will probably discover forms of movement, structures, and cosmic phenomena that remain completely hidden from us today. Just as previous generations couldn't imagine galaxies or expanding space, perhaps right now we are unaware of realities that future astronomers will consider obvious. The history of science repeats the same lesson continuously. Every answer reveals bigger questions. Every horizon hides another horizon beyond it. Every discovery expands the scale of the unknown. If someone asked, "Now, at what speed are you moving?" the most honest answer wouldn't be a number. It would be the acknowledgement that you are part of several journeys at the same time. Journeys that range from the rotation of your planet to the expansion of the observable universe itself. You travel through a cosmos so vast that even the most powerful telescopes can reveal only a fraction of it. And you do this while sitting perfectly still, carried by layers of movement so immense and so intertwined that they turn an ordinary moment into one of the greatest journeys ever conceived. Returning to the simple question that started this journey, at what speed are you really traveling through the universe? We've reached a point where the answer is no longer just a collection of numbers. It's no longer about kilometers per hour, orbital speeds, or the movement of galaxies. The deeper answer is that you exist within a universe where motion is woven into the very fabric of reality itself. Every moment of your life has unfolded aboard a planet that never stopped spinning, around a star that never stopped traveling, within a galaxy that never stopped moving through the cosmos. And maybe that's what makes the night sky such a fascinating world. When you look up, you're not facing a static image frozen in time. You're facing a universe in motion, a universe that has been evolving for billions of years and will keep evolving long after your chapter has ended. The stars above you, the galaxies beyond them, and the vast cosmic structures stretching across distances almost impossible to visualize, are all part of the same monumental story. What may be most remarkable is that amid all this motion, amid all this scale, a small species on a small world became conscious enough to ask questions about its own place in the cosmos. We learned to measure the movement of planets, to track the path of stars, to map the structure of galaxies, and to study the expansion of the universe itself. In doing so, we discovered that reality is vaster, stranger, and more beautiful than any previous generation could have imagined. The next time you go out on a quiet night and look at the stars, there's a simple fact to carry with you. You are not standing still. You are moving through the universe on a journey that began long before you were born and will continue long after you are gone. Carried by the cosmos that never rests, never stops moving, and never stops revealing new mysteries to those curious enough to look. Every breath you take, every sunrise you witness, every moment you spend under the night sky, it unfolds aboard a world racing through space at incredible speeds, as part of a cosmic journey so vast that even the most powerful telescopes reveal only a fraction of it. And maybe that's the most beautiful realization of all. No matter how immense, complex, and ever-changing the universe is, you are not separate from this story. You are part of it, traveling along with it, and for a brief moment within the cosmic story, you are lucky enough to realize that this journey is really happening.